In this example, let's consider a distribution that generates bits. And a bit is either a 0 or a 1. So for example, here's a bit sequence, 1, 0, 1, 1, 1, 1, 0. And we're going to assume that this was randomly generated by some probability distribution of x's that are independent and identically distributed, meaning that if the first digit is a 0, that in no way has any impact on what the next digit is. And our random variable in this case, rather than being, the vector is essentially a 1 by 1, it's either going to produce a 0 or a 1. And we will show that such a distribution is a member of the exponential family. So in this case, our x is, again, a single input. So what we have is a single parameter that will dictate whether a 1 appears or a 0 appears. So that's not necessarily just the probability. Just as with the normal distribution being part of the exponential family, the parameters themselves, the theta 1 and the theta 2, they were not actually mu and sigma, they were functions of mu and or sigma. And so in this case, the theta that we get is somehow going to influence how likely that value of x is, but it will not necessarily be the probability itself. So let's get into this a little bit more. Let's create some definitions for this. So in our case, h of x, which by the way, I'm going to not use the vector hat because again, it's a single scalar, so not necessary. And this is often a challenge as far as picking these functions when we are building them. So to be able to just take off with this is not necessarily trivial. Finding these functions in different circumstances sometimes involves more tedious processes. But in this case, h of x, remember that places volume on x. So in our case, because an x of 0 is not more or less likely than a 1, we will just say that these will both map to an equal weight. Okay, so now what about t of x? Well, t of x, we have to ask ourselves, and again, this is going to be 1 by 1 input and a 1 by 1 output. So I will omit the vector notation. T of x is a sufficient statistic, and that sufficient statistic has to be a statistic that is sufficient in fully specifying all of x. In this case, it's just a scalar, and so it's going to be either 0 or 1. Now, in this case, in order to fully specify whether the output will be 0 or 1, we actually just need to know the value of x. I'm not going to be able to know whether the output is a 0 or a 1 without just knowing whether the output is a 0 or a 1. Now, in some cases, the sufficient statistic may not just be the data itself. In this case, it is the datum because we need to know what it is. All right, I know this sounds somewhat vague, but let's build it from here. So theta is going to be some parameter, in this case some scalar, and for all intents and purposes it's just theta, right? We can figure out what theta needs to be when we plug it all in. Okay, so far we know that f of x comma theta, we know that this is going to be 1 over z of theta times h of x, which is just 1, times e to the t of x, which is x, times theta. And now what we need to know is what is z of theta. So z of theta is going to ensure that the sum of probabilities is equal to 1. So how do we get this value? Well, z of theta, if you notice that what we need to have is for, back up here, I'll do this in a separate color. If I, in this case, am dealing with discrete values, I'm going to use a discrete integral or a summation for x in the set 0, 1. The sum of these probabilities, in this case the PDF is a probability mass function, so each value is going to have its own probability, and this is going to equal 1. So that has to equal 1. So then if you multiply z of theta, because it doesn't depend upon x, so you can factor it out of the sum and then multiply both sides by z of theta, which will give us z of theta on the right, which I'll just go ahead and write over here on the left, equals e to the sum for x in the set 0, 1 of e to the theta x. Okay, so what I'm going to do is I'm going to add these up, and I know this needs to equal, this is what z of theta will be in order for the sum of the probability mass function probabilities to equal 1. And so that means z of theta will equal, well, it'll be e to the theta times 0 plus e to the theta times 1. And that means that z of theta will simply be e to the 0 is 1. This is e to the theta plus 1. Okay, so that means that what we have now is our probability mass function, f of x comma theta equals 1 over e to the theta plus 1 multiplied by 1 multiplied by e to the theta x. All right, so that means that if I want to know, given theta, now rather I should point out that this should be x given theta. So we can find the probability of x given our value of theta. So if I want to know what's the probability that x is 0 given theta, well, that will be 1 over e to the theta plus 1 times e to the theta times 0, and e to the 0 is 1. So the probability that we will get a 0 by randomly drawing from this distribution, either a 0 or a 1, will be 1 over e to the theta plus 1. All right, so dependent upon the value of theta that we give it, this will be the probability. And if you take the probability of x being a 1 given theta, that'll be e to the theta, so plugging in 1 for x, and 1 times theta is theta, over e to the theta plus 1. Now, by the way, we could have just used, since this is a discrete probability, we could have just said the probability that x equals 0, the random variable given theta, and the probability that capital X equals 1 given theta. So given theta, if I give you a theta, then you can find the probability of generating a 0 versus generating a 1. So it's all about the choice of theta that we pick. Now notice that if you add, f of 0 given theta plus f of 1 given theta, well, we forced the sum to equal 1, but this, just to verify, will be 1 over e to the theta plus 1 plus e to the theta over e to the theta plus 1. And when you add those together, you get e to the theta plus 1 in the numerator, e to the theta plus 1 in the denominator. Those cancel out and give us 1, which is exactly how we picked z of theta. So that's just a great check to make sure that that worked out. Now, as far as what we might expect, well, maybe we want to generate a 0 1/2 of the time. So that, notice, doesn't necessarily correspond to a theta of 1/2, because if you do e to the 1/2 plus 1, you're not going to get 2, and the fraction won't just be 1 over 2. But if you wanted f of 0 theta to equal 1/2, for instance, I want that to be true. Well, that means that I need 1 over e to the theta plus 1 to equal 1/2. And, well, that will tell me that I need the denominator right here to equal 2. So e to the theta plus 1 equals 2, which means e to the theta equals 1. Taking the natural log of both sides, theta equals the natural log of 1, and that is equal to 0. So if you pick theta equal to 0, then that will give you a probability of 1/2 of picking x equals 0. And also, at the same time, if theta is 0, then that means we'll have 1 over 1 plus 1. That will also give us a 1/2 probability for drawing an x value of 1. Now, as far as what we've just established here, we have written as an exponential distribution, or as a PDF that is part of the exponential family, we have now written a function that is part of the exponential family and simultaneously models something where there are two events, binary, 1 or 0, and that is called a Bernoulli distribution. So in our case, f of x theta, or f of x given theta, which is equal to, we said, e to the theta x over e to the theta plus 1. This is what we call a Bernoulli distribution with parameter theta. Now, as far as converting that to a probability, that's a whole nother scheme, but if theta equals 0, we'll get a 1/2 probability on both sides. So we just observed that being part of an exponential family doesn't just literally mean that. It means that there are other distributions that fall under the umbrella of the exponential family. And here's just a partial list. If you were to pick h of x equals 1 over x, and t of x equals the vector log x and log of x squared, with our parameter set being theta vector equals theta 1, theta 2, because there, notice, are two functions of x here, so we'll need two parameters, and that will form what we call a log normal distribution. And if you integrate that from 0 to infinity, then you calculate your z of theta. And all of these distributions that you see here, some of them may look familiar, some of them may not. An actual exponential distribution would involve basically just using e to the theta x and chi-squared, beta, multivariate, normal. We already saw the normal as an example of exponential family, as well as gamma, the gamma distribution. And so there are other different types of distributions we can form, but these are just some of the more common ones. Now, as far as picking the t of x, again, not super trivial. As another example, suppose that we had information on, say, 3 random variables, and maybe what we knew for a fact was that these had to sum to 20. That x1 plus x2 plus x3 had to sum to 20. Well, in this case, your t of x, your sufficient statistic, if we think about what that would be in this case, well, what would be sufficient information to fully infer the vector x? Well, I wouldn't need to give you, remember, this is a vector, and it's going to take in x1, x2, x3. In order to know what those 3 values are, what is the minimal amount of information I would need? Well, if I don't give you x3, you can certainly infer it from the fact that x1 plus x2 adds up to 11, and adding x3 to it must give me 20. So that means that a sufficient statistic in this case would just be x1, x2, right? Because from that, I would fully know what x3 has to be, and that was what we would consider to be a sufficient statistic in that case. So because of the schema here, it sufficed to know just the value of two random variables without having to know the value of the third. In our case up here, well, the output is a 0 or a 1. There's no lesser information that we can require other than whether it's a 0 or a 1 in order to know whether it's a 0 or a 1. In order to know what x1, x2, and x3 are, we only need to know two of the values. That's sufficient to encapsulate what that third value should be as well.